Now, we have seen that what are the properties, and here in this particular lecture, we are just talking about agent 0 and PLACA. Now, when the agents need to be communicating with each other, they will have certain sets of beliefs and desires. And as a result of which, they have a language which is basically called as a agent-oriented programming language. Because when they're communicating with each other, they will be sharing some particular content. So it is very important that there needs to be some particular protocol and method by the way these particular agents will be communicating with each other. So we have this AOP, which is basically the agent oriented programming language. And the first agent which was created using the agent oriented programming language was agent 0. PLACA is basically improvisation of your agent 0. And as you can see over here, there is a paper which is basically referred, and it says that PLACA is an agent-oriented programming language developed in around 1993. And since each of these particular agents have their own beliefs, their own desires and intentions, right? So the other agent should be knowing what is the belief and the intentions of the other agent. Now, AOP is basically a new programming paradigm, which is basically based on the societal view of computation. And it embodies basically the strong notion of an agency. Now, the key idea that informs that the agent-oriented programming is directly programming agents in terms of their, beliefs, commitments, and intentions. Like I already told you that the agents have their own beliefs, commitment, and intentions, and it is very essential that one agent should know about the belief and the commitment and intention of the other agent before they actually start doing the communication with each other. Because in a multi-agent environment, there needs to be many agents which need to be communicating with each other. Now, the key idea that informs AOP is that of directly programming agents in terms of their beliefs, commitments, as well as intentions. So, this particular programming language basically takes care of all these particular terms which are associated when agents need to be communicating with each other. Now, the motivation behind such a particular proposal is that we already know that there is something called as an abstraction mechanism like we had in the object-oriented programming. Similarly, even in the agent-oriented programming language, we have this particular mechanism of abstraction, which helps us to, uh, have a communication environment for the particular agents with their own beliefs, commitments, as well as intentions. In the same way that we use the intentional stance to describe humans, it may be useful to use that same particular intentional stance to program machines. So every particular human has their own intentions, commitments, right? So basically, these particular programming language is helping us to, describe these particular machines similar to your humans. Now, this particular researcher, Shoham, basically suggested, so he was a person who actually developed this particular programming language, that is AOP. And he suggested that a complete AOP system will basically have three main components. That is, first one is a logic, which is basically used to specify agents and also to describe what their current mental state is there. A programming language for programming the agents, which will basically be an interpreted programming language. And next, an agentification process for basically converting the neutral applications into agents. So basically, if we can take the database also can be considered as an agent. So it is agentification is basically a process wherein you would be converting any particular normal program into you know, an agent-based type of program. Okay. Now, results only reported that on the first two components, that is the relationship between logic and programming language is semantic. So we will skip over the logic and consider the first AOP language, which is basically agent zero, right? So as I told you, agent zero is the first AOP language, and PLACA basically follows it. Now, agent zero is implemented in an extension of Lisp, which is basically a programming language, uh, which has been used for programming with agents and AI, right? So each particular agent in agent zero has four components. It has a set of capabilities, that is what the agent can do, an initial set of beliefs and initial set of commitments, that is things that the agent will do, and a set of rules, okay, which we basically call as the commitment rules. Now, the key components which determine how the agents act is the commitment rule set. Okay, now each particular commitment rule. Now, as we have seen here already, that the main components, commitment rule is one of the main components which is there for this particular agent zero, which is implemented using your agent oriented AOP language. Now, every particular rule is going to have uh, a message condition, what will be the mental condition, and what is the action which needs to be performed, right? So on each agent cycle, the message condition is matched. So whenever the agents are communicating with each other, say if agent A is communicating with agent B, right, what would be happening is whatever would be the message condition, it will be matched against the messages that the agent has received. Okay, say A communicates with B and it says hello. Okay, now that particular message would be compared with whatever message conditions have been defined in the commitment rule, right? So the mental condition is then matched against the belief of the agent. Okay. So the first thing is that the message condition will be matched against whatever message is being received. Second is the mental condition will be matched again. Now, every particular agent will have some set of initial beliefs, right? So that is what is basically called as a mental condition. Now, why does it say mental condition? Because if we generally talk with respect to your human scenario also, right? Um, every particular human being has his own belief system with respect to any particular situation, right? And when we receive that particular input from our environment, right, we think based on the belief system we have. So similarly, it is even for the agent, right? So the mental condition is already been defined, sorry, the belief of the agent has already been defined, and that is matched with this particular mental condition. Now, if the rule fires, then the agent becomes committed to the action. So in case if both these things fall into place, right? So the message condition is what uh, is basically matching with whatever the message has been received, as well as the mental condition is matched against whatever his belief is there. So when these two conditions will match, that's where then the agent then needs to perform the corresponding action, right? So basically, when I say the corresponding action needs to be performed, so it's that's why it is told in this particular line that the rule fires and then the agent becomes committed to do that particular action. Action can be private or it can be communicated. That is basically sending messages. Private can be, which may be corresponding to, it may be that once it receives a particular message, it needs to do some particular subroutine, basically a small function execution needs to be done internally. So that action would be called as your private. Now, the messages are uh, constrained to be of the three types. One is you can have a request message, that is to commit to the particular action. You can have inform message, which is basically just passing on the information. You can have an unrequest, that is basically to refrain from the action. That is, uh, you do not want that once the messages are received or the belief systems are matched, that some particular action needs to be taken for it. Okay. Okay. Just let's see this particular block diagram. So as you can see over here, uh, we have this initialize, then we have, so we have over here, this is my agent. which you can see, which I'm pointing out. So it has its own beliefs, commitments, and its own abilities, right? Uh, Now, based on whatever my initial message is being received, it may be updating its beliefs and corresponding, it may be updating its commitments, right? So, and then corresponding, it does the execution and then it goes back here again, okay, wherein he may again need to require to update his particular beliefs. So we'll see that in the forthcoming lectures. Okay, so how is it that we actually specify the particular rule? Now, coming back to this particular part, we said that, commitment rule is one of the major components which is there. And a commitment rule is going to have a message condition, it's going to have a mental condition, and it is going to have an action. Okay. So when we write it in terms of the programming part, right? So here is basically a code snippet which defines to me. So here's where the commitment rule is. So the commitment rule is that the agent requests that you do a particular action in a particular time. Okay. And now we have this particular agent B. Okay. And now it is a friend agent and can do an action, and it can, do the particular action at a particular time, right? So what is the, mental state, right? And what is the okay, so what is the current mental state, right? So based, it is being matched with the particular belief system, right? And can correspondingly perform the particular action, right? So you can see over here, these have been given as comments. So this is basically what would be my message condition. This would be my mental condition, which is there of the particular agent. Okay. Now this rule may be paraphrased as follows. So we are basically describing this. So if I receive a message from agent which requests me to do an action at time, and I believe that agent is currently a friend, I can do that action at time, and I'm not committed to doing any other action. So at a particular time, if this particular agent approaches me, so then in that case, I am his friend. I will do the particular action. That's what this particular example code snippet basically describes as. Now, this example basically gives a flavor of how your Agent Zero programs are. Okay, so Agent Zero basically provides support for multiple agents to be cooperating and communicating with each other, and also provides provision for debugging. It is, however, just a prototype that was designed to illustrate some principles rather than be a production language. Uh, then we had Agent Zero being further refined, and it was called as a PLACA, right? Now, PLACA is basically the full form as Planning Communicating Agents language, which was basically intended to address whatever drawbacks was there of Agent Zero, that is the inability of the agents to plan as well as communicate request for actions via high level goals. So in your Agent Zero, there was no planning which was done when the before the agents actually start communicating, right? So that is being taken care in PLACA. Now, agents in PLACA are programmed in the same way almost as a agent zero, in terms of where I call the, mental associated rules. So the little difference which is there when I see with respect to PLACA is an example mental change rule is basically discussed here. So he's basically showing an agent which requests a particular activity to be done, right? So say for example, it needs to do the Xerox operation, and it is said that and can achieve it in this much particular time, right? Now BEL basically is the belief system of the particular agent, and the intention is that the Xerox basically happens at 5 p.m. Okay, so let's just go through as to what this has been paraphrased as. Now, if someone asks you to Xerox something and you can, and you don't believe that uh, they are a VIP or that you're supposed to be shelving books, then adopt the intention to Xerox it by 5 p.m. and inform them of your newly adopted intention. Now, say for example, an agent is doing some other work, right? And he cannot take this particular task up at 5 p.m. because he's already having a task in hand at that particular time. Then in that case, the agent would inform that it cannot take up this particular task. But if the request has arrived and uh, you think that this particular thing can be taken up, right? And uh, it is not a very important that the particular agent is not doing a very important task, and uh, it doesn't require any booking as such, then in that case, this intention would be changed. Okay, now here is where, so the agent has basically been designed such that, it will first see whether it is available or not, right? Does the task require some particular booking? Is it a very important task, right? So all these things would be, so the agent has been defined such that is the mental rule of it has been defined. Okay, but now the request which is being sent is that it wants that, the Xeroxing should be done at 5 p.m. So now it needs to adapt to this particular new intention. Okay. Coming to concurrent meta. Okay, concurrent meta TEM. Okay, this is basically a multi-agent language in which each agent is programmed by giving it a particular logic, temporal logic. Now, temporal logic is basically a logic which is based to be occurring at a particular time. Okay, it is specification of the behavior it should exhibit at a particular time. So let's say that if it needs to do a Xerox operation at 5, means it needs to do the operation at 5. Okay, now these specifications are executed directly in order to generate a behavior of the agent. Now, temporal logic is basically a classic logic that uses modal operators for describing how the truth of proposition changes over time. So if I may say that, okay, the job as of now, if I say, okay, yeah, the job can be done at 5 p.m., right? So that truth applies now. But maybe 1 hour later, that truth would not be valid, right? So uh, this particular language, okay, uh, Meta 10 is a multi-agent language which basically takes into consideration the time factor. That's the reason we augment to the modal operators, which is actually being used for your intelligent agents. So, for example, as you can see over here, it says important agents. Now, if I have a square box, okay, so what does it mean? Now, these are basically symbolic notations of your modal operators. Now it means it is now and will always be true that the agents are important. Okay. When I show a diamond, it means that sometime in the future that particular agent may be important. When I have, this with diamond with a black dot, it says sometime in the past it was true and that prologue was important. Okay. So if I have this particular function important, right, then in that case, that's how we will be defining it in terms of modal logic. Okay. If I have something like this, not friends, us, you, apologies, you. Sometime in the past, it was true that prologue was important. Okay. Okay. So basically, this explanation holds for this one. Uh, Just let's once again just say this. Okay. So it is now and will be true that agents are important. This implies for this. This implies that the diamond symbol, it sometimes in the future it will be important. Uh, this describes that sometime in the past it was true and that prologue was important. Coming on to this particular logic, okay, we are not friends until you apologize. Okay, so not friends, apologize you. Okay, uh, apologize you means tomorrow you apologize. Okay, so this circle notation basically uh, tells me of the next state, which is basically tomorrow. Okay. So it is basically it is a framework for executing the temporal logic specifications. Now the root of the concept is Gabbe's separation theorem, which basically says an arbitrary temporal logic formula can be rewritten into a logically equivalent past future form. Now, this past future form can be used as execution rules. A program is a set of such rules. The execution proceeds by a process of continuously matching these rules against a history and firing those rules whose antecedents are satisfied. Okay. Now, the main underlying concept of this has been actually defined by Gabbe in the separation theorem, which says that the temporal logic formulae can actually be rewritten uh, logically as a past future form. Now, this past future form is actually the execution rules, right? So, a program will be uh, a set of these particular past future form of rules. Okay. So execution will be proceed by a process of matching the rules continuously against a history and firing only those particular rules whose antecedents are satisfied. Now the instantiated future time consequence become commitments which must subsequently be satisfied. So the past thing would be that it would refer to that and it will, match it, okay, for doing the execution. But for doing a future event, right, the future form would basically become a commitment. Okay, that means it subsequently needs to be satisfied. Now, execution is thus a process of iteratively generating a model for the formulae made up of the program rules. Okay, so we would be making these particular execution rules, okay, and say for example, okay, the future time parts of the instantiated rules basically represent constraints of this particular model. So you would be making a model, and that particular model would have a certain set of rules, which will be defining the past and the future, and the future time parts of the rules would basically represent as the constraints that is beyond which the system would not go. Okay, now an example program. Okay, let's say we have an example program that is basically a resource controller. Okay, and this symbol uh, represents for all x. Okay, ask. So if x is going to ask something, uh, the state would be that you need to give. Okay, now if it is for all x and y, give of x and give of y, x is equal to y. So let's just see what this rule says. The first rule ensures that an ask is eventually followed by a give. So it's basically that if you're asking something to the agent, right, they're going to give it to you. Next is second rule ensures that only one give is ever performed at any one time. There are algorithms for executing programs that appear to give reasonable performance. There is also separated normal form. Okay, so now the second statement basically or second rule ensures that only one give is performed at any one particular time. Okay. Now it provides an operational framework through which societies of processes can operate and they can communicate with each other. And it is based on the new model for concurrency in executable logics. Now the notion of executing a logical specification to generate individual agents' behavior. Now, system can, for example, contain a number of agents, right, which are basically like objects. That's the reason when I talked about that the first programming language which was there for making the agents communicate with each other was agent uh, oriented programming language. Okay, so these agents are basically considered as object, and each object has basically three attributes. Like uh, if you know your a basic object oriented programming language is going to have a name, okay, it's going to have an interface, and it's going to have a program. Generally an object basically has properties, methods, right, and yeah, so it's going to have properties, methods, set of actions which you need to perform. So here's where an object has these three attributes. That is, an object going to have a name by which you're going to refer it. it'll have an interface, okay, through which the the methods of the particular object will be accessed, and it'll have a program. An object interface contains two sets. One is environment predicates, and these correspond to messages the object will accept, okay, and component predicates, which basically correspond to messages the object may send, okay. So, so there are two types of predicates, okay. For example, a stack object interface, okay. So stack pop comma push, popped comma stack full. So what these basically indicate? Now here pop and push are basically environment predicates, and these correspond to messages that the object is going to accept. So the object is stack and it is going to accept these two as the inputs, right? And the popped and stack full is basically the component predicates which correspond to the message that the object may be sending, right? If an agent receives a message headed by an environment predicate, it accepts it. If an object satisfies a commitment corresponding to a component predicate, it broadcasts it. Right? So these are the two things which an agent basically does. So if an agent will receive a message which is being headed by this environment predicate, right, it's going to accept it. And if it satisfies a commitment corresponding to a component predicate, it, then in that case, it will be broadcasting it. So based on whatever is there ahead, it does the particular operation. To illustrate this particular language in more detail, here are some of the examples. For example, we have Snow White has some sweets, which is basically resources, which she will give to the dwarfs. This is the resource consumers. Now she will only give to one dwarf at a time, right? And she will eventually give it to a dwarf that asks. So here is Snow White is written in this particular form. So Snow White. So this is my basically the object of the agent. Okay. So if Snow White asks, right, so this particular agent will give. So if you can see up here, you have in circular brackets ask, right? So this is basically a request which it needs to accept. And if it is ask, then if a dwarf asks an X at a particular time, then in that case, Snow White is supposed to be giving. Next is give X and give Y. Okay. She will eventually give to a dwarf that asks, right? So this is wherein she will only give one dwarf at a time, right? And this is that she will give to a dwarf that asks. The dwarf the dwarf eager asks for sweets initially, and then whenever he has just received one, he asks again. So I have this agent which I call it as a dwarf because this dwarf is dwarf eager. So give and ask, and uh, it asks for sweets initially, right? So it's basically ask eager, right? So the agent is being the agent asks basically, and here is basically that whenever he has just received one, he asks him. So whenever he's given, he asks again. So give eager, ask again, right? So some dogs are even less polite, greedy, just like every time. So we have another agent, greedy, give and ask. Okay? In that we will have ask all the time. Okay? So in that case we use this. Fortunately, some have better manners and are courteous and only ask when eager and greedy have eaten. Okay? Okay, so we'll stop here. In next session, we'll continue the remaining.